Hi students, welcome to Alpha's e-learning chemistry classes for second year. The running chapter is electrochemistry and now we are in session number 9. Before entering into the topic in this session, let me give a brief review of the previous session discussions. Clear? It is nothing but the effect of dilution on conductances of the weak and strong electrolytes. Weak and strong electrolytes, where the dilution will affect both kappa of these two as well as lambda or mu of these two, and how the dilution is affecting this. And for that purpose, first of all, kappa, if you recollect, it is depending only on the number of ions that present per ml. And present per ml, that is for unit volume, how many number of ions present, that is responsible for specific conductance. And whereas lambda or mu, it is directly related to total number of ions, present in the solution. Present in the solution. Here the volume is not confined, you remember. So these are the number of ions per unit volume is responsible for specific conductance, the total number is responsible for this conductance. And now let us look at this strong electrolyte. Strong electrolyte is nothing but which undergo 100% ionization, you know. And when it is already in 100% ionization at certain concentration, if the dilution is happened, the same number of ions will exist in the solution. But the number of ions per unit volume of the solution before and after dilution will change. Before dilution it is having more number, and after dilution per unit volume the number will decrease. That's why in case of strong electrolyte, kappa will decrease. And now coming to weak electrolyte. In case of weak electrolyte, as per Ostwald's law, alpha, that is degree of dissociation, is directly proportional to square root of dilution. And with this scenario, automatically when this dilution is happening for the weak electrolyte, the dissociation will increase and thereby the number of ions will increase with increasing the dilution. But still it is having kappa decrease. That means even in case of weak electrolyte also, on dilution the specific conductance decrease. The reason behind already we know. When compared to this increase in number of ions and the increase in volume, the increase in number of ions is relatively very less compared to the increase in volume. So because of that, again the number of ions per unit volume after dilution also coming down even for weak electrolyte. That is the reason for decrease in kappa, that is specific conductance of the weak electrolyte. Clear? And now coming to this. Here it depends on the total number of ions present in the solution. In such a case, in case of strong electrolyte, already where the electrolyte is completely ionized or dissociated, no further increase in number of ions is observed on dilution. And when there is no further ion generation, automatically the number of ions will create a saturated conductance. That will happen. We may think like that, but even then, here also we observe that the conductance in dilution first slightly increased a little extent and then it becomes saturated or then it becomes constant. And here if you recollect, the reason behind is nothing but before dilution the ions are under some sort of interionic attractions. And because of that interionic attractions, they are having less mobility and thereby the conductance is less, and as the dilution is going on, that interionic attractions are ceasing or they are decreasing, and thereby it is reaching to where the interionic attraction becomes zero, there the conductance becomes saturated. And unlike that of this, in case of weak electrolytes, as per this, as the dilution increases, the degree of dissociation continuously going on increase. And you remember, once again you remember, weak electrolytes will never undergo 100% ionization at any dilution practically. If practically it is possible to make it to go for 100% ionization or dissociation, then it is no more weak. Now it becomes strong. That's why theoretically we can imagine the 100% ionization of weak electrolyte, but practically we can't find that. So here, as the dissociation increases with the dilution, the number of ions increase, and thereby in case of weak electrolytes, the conductance is continuously goes on to increase. This is what we discussed in the previous session. And now if we draw all these relations in a graph that drawn between the conductance and the concentrations, like this, they appear like this. It is the graph y-axis where we are taking the conductance of the electrolyte, and in this one we are taking square root of concentration. And you remember here the concentration becomes 0, means all this electrolyte is completely dissociating into ions. It becomes 0 and these two become maximum. In this condition, the concentration of electrolyte is said to be 0. So when all the ions are, all these molecules are completely dissociated, then the conductance becomes maximum. That is known as the conductance at that condition is known as conductance at infinite dilution or conductance at 0 concentration. Already we discussed it in previous sessions also. And now if we draw the graph between these two for different electrolytes, they appear like this. It is for KCl and it is for most frequently used in most of the books. They are giving the same. That's why I am also providing the same. It is nothing but Na2SO4 like this. And then for weak electrolyte like CH3COOH. If we observe these graphs, we can say that irrespective of the chemical nature of these electrolytes, chemical nature means it may be acid or it may be sometimes base or it may be salt, irrespective of that, the conductance is purely depending on the type of the electrolyte, whether it is strong or weak electrolyte. And from this we can say that the decrease in conductance with the increase in concentration, just you observe, decrease in conductance with increase in conductance with increase in concentration follows the order. It is nothing but strong, univalent. Best example is KCl. And then it is strong, bivalent or strong univalent. It is nothing but BaCl2 or Na2SO4. I think you know about these two words. Uni means unity is 1, bivalent means 2, either -2, -2 or +2, these two are bivalent, and if it is -1 or +1, it is nothing but univalent. And then it is strong bivalent. That means both the two ions are having minus and plus +2 and -2, like that. And then this is having less and it is having less and it is having less. That is nothing but weak electrolyte. This weak electrolyte is CH3COOH. Here you observe, actually what we are writing the trend in here is decrease in conductance with increase in concentration. Decrease in conductance with increase in concentration. We are coming in this direction. Concentration is increased in this direction. The decrease is less in case of univalent, and thereafter the decrease after this, that means when compared to univalent, the decrease is more in case of this, and the decrease is still more in this, and simply you can observe this decrease is more and more in case of strong electrode. With this comparison you can understand this concept, I think. And when we are moving like this, in all these cases some sort of decrease we can't observe with this slope actually practically here, but you can understand this concept simply by observing this. Now we are coming like this, and in this case when the concentration increase, the decrease is more, that what we are reflecting here. Simply this is clear, and this is the order that we can find when we draw the graph between the conductance, it may be molar or equivalent conductance, and the concentration terms. Clear? And now theoretically, and that means theoretically we are drawing this, and the actual relation, experimental relations, we can find these experimental relations to find the conductance of electrolytes at infinite dilution or at zero concentration. We can use Debye, Haeckel, Unsager equation. Debye, Haeckel, Unsager equation. That is one of the law. And how we are applying that? What is Debye, Haeckel, Unsager equation, and how it is useful in finding the conductance of the electrolytes at infinite dilution, where it is useful, where it fails, or if we have to discuss in this session. Clear? And now let me give that. Debye, Haeckel, Unsager equation. Experimentally he has given a theoretical formulation for this conductance relation with dilution in the form of equation, which is written as lambda m is equal to lambda naught m minus a plus b lambda naught m into root c. This is the actual relation given here. A and b, these two are Debye, Haeckel, Unsager constants. Debye, Haeckel constants. And simply in a short form we can write this like this. In a short form we can write this as lambda m is equal to lambda naught m minus b lambda naught m under root c. Like this we can write. Clear? And now, and when it is here, the b is nothing but a constant. That constant depends on the nature of, again you remember this constant b in short form of Unsager equation depends on nature of solvent as well as temperature. Nature of solvent and temperature. And for your convenience sake, let me give the b value in case of the frequently used solvent. What the frequently used solvent is nothing but water. That is in case of aqueous solutions, aqueous solution. And the temperature, let us consider room temperature, that is 25 degrees, that is 298 Kelvin. Clear? Here this form, that is lambda m is given as lambda naught m minus 60.2 plus 0.229 lambda naught m into root c. This is the Unsager equation for aqueous solutions at 25 degrees centigrade. Clear? And this value, this is nothing but the b value. And with this relation, if you observe in any of these cases, it is variable. Clear? And it is variable and it is variable. And when these two are present in this case, we can observe, we can rearrange it to get into a straight line equation. Y is equal to minus mx plus c. We can rearrange that like this. Let me write that rearranged equation. It is lambda m is equal to minus a plus b lambda naught m root C plus lambda naught m. Or this we can write lambda m is equal to minus b lambda naught m root C plus lambda naught m. Or for water we can write lambda m is equal to minus 60.2 plus 0.229 lambda naught m root C plus lambda naught m. This is, all these are here. On y axis this variable condition, on x axis this is the variable condition, that is root C, what we draw in the previous graphs, and this lambda naught m is nothing but intercept on y axis with a negative slope of these values. So why I wrote all these equations are nothing but simply they are not asking, or they are not, in general they are not asking for any numericals from this Unsagr equation, just they are asking which of the following is the correct form of Unsagr equation, and from this Unsagr equation which is intercept, which is slope, what is the value for aqueous solution, what is the slope of this graph, like that. So with this, when we draw the graph between lambda m and root C, again let me draw the graph. It is lambda m and it is root C. And for strong electrolyte, let me draw only two, because thereby we can understand what is the concept of Unsagr equation. It is the graph for KCl, which is supposed to be of a strong electrolyte. Clear? And now this is the graph that what we are getting in case of weak electrolyte, that is nothing but CH3COOH. Now in case of strong electrolyte, which is of obeying that straight line equation like this, and where the slope is nothing but slope is negative, it is coming like this. And now we can get this conductance at infinite dilution, that is nothing but at zero concentration, by extrapolating technique, where if we are extrapolated this graph, it is of intersect this y axis, that is a conductance axis, that is nothing but lambda naught m. So with that extrapolating technique means we are getting at different concentration the conductance we are measuring by that is nothing but a sequential time intervals like this, and after that, after getting, when we are extrapolating that at zero concentration, that is where KCl is supposed to undergo 100% ionization, the conductance is here, that is lambda naught m. So this Unsagr equation, with this Unsagr equation we are able to measure or calculate the conductance at infinite dilution with this technique from experimental results. And now let us try to get this for this weak electrolyte. Let us try to get this. And now I am trying to get that extrapolating, but if you observe that extrapolating technique is not working here, because in case of weak electrolytes, even though it is slowly increasing to some extent, all of a sudden at certain dilution, this is dilution, decrease in concentration, this graph is shoots up and it is running parallel with this conductance axis, and when these two are going parallel, it is not at all possible to find any intercept practically. Extrapolating technique is not working here. That's why in case of weak electrolytes, this Debye-Huckel-Unsagr equation totally failed. That's why it is not useful. That means altogether previous discussion also it is same. For weak electrolyte, it is not at all possible to measure the conductance at infinite dilution practically. Here it is proved. because when the dilution is going on, the dissociation increase and it never go in a straight line manner. That's why practically it is not possible to measure it. And one more is here, even though Debye-Hackel Ansagari, it seemed to be useful, it seemed to be applicable for these strong electrolytes. Okay, no doubt at all. At strong electrolytes it is applicable, but it is also having some difficulties, that is some deviations at higher concentrations. And now the competitive examination question will be on that one, as we know, because these two are familiar concepts. That Ansagari equation is useful in finding the conductance of the strong electrolyte at infinite dilution, and it totally failed in case of weak electrolytes. But the question what they are framing is in a logical approach. Though from Ansagari equation we are able to find the conductance of the strong electrolyte at infinite dilution, it is of observing some deviations in case of strong concentrated solutions. Do you know the reason? It is applicable, no doubt at all. It is applicable for strong electrolyte, but when concentration increases for strong electrolytes also, it is of exhibiting some sort of deviation from the regular, that is nothing but straight line equation. We should know that. Actually, practically, if we observe, that is happening. Now the question is whether that is happening or not. They are not asking like that. Do you know the reason why it is exhibiting the deviation? That is the question. Here again, the same concept, that is nothing but the deviation from this regular, that is straight line equation of strong electrolytes from Ansagari equation is only because of interionic attractions. Because of that interionic attraction. Now, if you recollect the previous class, we are going there from interionic attractions, we are relieving that interionic attraction slowly at certain conditions like this. And after reaching this, it is maximum. Previous. And now we are coming this. The question is asked in a different approach. So when they are asking the question in a different approach, we should not get any confusion. Just you observe. It is this Debye-Hackel Ansagari equation is applicable for strong electrolyte, no doubt at all. When we are taking the extra plotting technique, we are able to get the conductance of the strong electrolyte at infinite dilution. That is the saturated condition, because it is intercepting this, that is intersecting the conductance axis. But that strong electrolyte where we are supposed to have this Debye-Hackel Ansagari equation application is also exhibiting some sort of deviation from its regular, that is straight line equation at high concentrations. The reason behind is at high concentrations, again this is the reason, interionic attractions. So now in case if interionic attractions are responsible for deviations, for which type of at what concentrations we can apply the Debye-Hackel Ansagari equation? That is one more question. At what concentrations we can apply Debye-Hackel Ansagari equation for finding the infinite dilution conductance for strong electrolytes? Simply you remember forever, it is in case of strong electrolytes when the concentration is less than or equal to 0.02 molar. That's all. If the concentration is greater than this, then you can find the deviation from this equation also, even though they are strong electrolytes. Are you clear with this one? And now, this is generally what we have to discuss in Debye-Hackel Ansagari equation, which is useful in finding the conductance of strong electrolyte at infinite dilution. But we find at the same time we are also finding that it totally failed to find the conductance of weak electrolyte. Then what is next? That means what is the source to find this weak electrolyte conductance at infinite dilution, which is supposed practically not possible? What is the source? Simply we are having a source for that. It is nothing but by applying Kohlrausch law. Kohlrausch law, we can find the conductance of weak electrolyte at infinite dilution, that is at zero concentration, which is imaginary only. The infinite dilution or zero concentration of weak electrolyte is imaginary, practically not possible. Even then, with the help of Kohlrausch law, we can find its conductance at infinite dilution. Clear? That will be discussed in our next session. Clear?